Alrighty, this lesson is going to be a brief conceptual overview of the second law of thermodynamics. Now, we're not going to go into the math deeply. Actually, we're not going to go into the math at all. I'm pretty much going to wrap up today, I'm going to wrap up thermodynamics with what we're going to go over today. Now, what we're going to start talking about here is the second law. Right now, with the second law of thermodynamics, there's a couple of different ways of stating it. All right, I'm going to go through the real life examples first, and then after that we are going to go into the overall situation, which has to do with entropy. All right, now I am using a website for some of my definitions here. I'm going to be using hyperphysics.phy. The site is right up here. It's really a great tool for a lot of different things. All right, now with the second law, there's two different real-life situations that we have to look at. First of all, the second law of thermodynamics says that, this is what's called the Kelvin-Planck statement of the second law. It's impossible to take all of your heat from your hot reservoir and send it all into work. This cannot happen. There needs to be some waste heat sent out. Now, the way that they explain it here is kind of like this situation right here. If you were to have a water wheel on a waterfall, now obviously that water is going to have more kinetic energy the farther it falls. Therefore, the further down you make this thing, then the more kinetic energy you're going to pick up. But the problem is, if you put this all the way at the base, you are going to lose a lot of that kinetic energy into the fact that this water is going to start having a horizontal motion as well. You're going to lose a lot of that fall. It's going to waste a lot of the energy, and then it's going to be gone. So, if you're constrained to put your water wheel halfway up the waterfall, then you can extract at most half of the energy available, because the other half of it still is in the last part of the fall. The closer you make this to the bottom of the waterfall, then the more overall energy you would be able to collect, until you get to a point. If you put it all the way at the bottom, then it obviously is not going to be spinning properly. Okay? Likewise, if you have a 600 Kelvin heat reservoir and dumping energy into a 300 Kelvin waste reservoir, the most efficient that you can pull out is a 50% efficient engine. Okay? Now, with the Kelvin-Planck statement, you can take work out, but you always need to have a cold reservoir. You need to have some waste heat. Okay? In other words, you cannot have a 100% efficient engine. It's impossible. Okay? So, the first situation of the second law tells us that it is completely impossible to have a 100% efficient heat engine. There's always going to be some waste. There has to be some waste. Okay? Now, that's the first explanation. Now, copy this down. I already had you guys do this the other day, but make sure that you have all of the definitions that I'm giving you here in your notes. The second situation is with refrigeration. Okay? Now, this one basically has to do with the fact that you cannot just take heat from a cold reservoir and naturally send it to a hot. We already said that hot heat will naturally flow from a high temperature to a low temperature, not from a low to a high. So in other words, you need to have work going in order to cause that heat to leave the cold reservoir and go to the hot reservoir. All right. Now, the other definition involving refrigerators has to do with this. Energy will not flow spontaneously from a low temperature object to a higher temperature object. All right. So in other words, you cannot have a perfect refrigerator. You cannot literally just send your heat from cold to hot. You need to do work in order for that to naturally happen. Right? Air conditioners, heat pumps, all of those are going to obey the same exact thing. This is what's called the Clausius statement. I'm not going to get specific into which individual statement is which, but you may have to distinguish between a refrigerator situation of the second law and a heat engine situation. Now, this is more of the overall view. Right? In any cyclical process, the entropy will either increase or remain the same. Now, first of all, entropy is literally, you can think about that as chaos. Okay, so let me flip back to the chart over here. Now, when we're talking about entropy, entropy is literally chaos. Now, I'm going to go back to that other page, but I want to talk about this briefly. Okay, with entropy is basically the tendency of the universe to move toward disorder. All right. Now, that's kind of the basics of the basics there. All right. The way that I like to think about this, when you're thinking about what entropy is, I like to think about that TV show Hoarders. Okay, if you look at those bedrooms, those living rooms, those garages, whatever, that are completely filled about 2 to 3 feet high with just garbage, junk, crap, well, the reason that that has gone towards disorder is there's been no energy used to try to keep that in a steady state. So if you were to do the same exact thing in your bedroom and not clean anything, not move anything, not throw anything away, over a period of several months, you would probably get to the point where you no longer have a floor. After you got to the point of a year or so, you probably would be walking on several inches of waste. Okay? Now, there's always a way to get rid of entropy, but the thing is, anytime that you try to get rid of entropy, you always have to do work. Now, here's the problem. When you do work, now I don't care if you hire manual labor or do it yourself. When you do work, you are applying a force that is going to cause some displacement. When you apply that force is going to have to be a result of some type of an energy transfer inside your muscles. All that lovely ATP stuff that Scarbs talks about. Transfer. Which is going to result in heat lost. So literally, your body is going to be a heat engine in this process. You're doing work, but there has to be waste heat. Now, when that waste heat is lost, that is causing the air molecules in the room to have a more random motion. So even though you are doing work to make the overall entropy of your room better, the thing is, when this heat is lost, it is increasing the overall entropy of the universe. All right? Stephen Hawking wrote in his book, A Brief History of Time. It's a really good book. It's a relatively short read. It's only about 180 pages. If any of you guys are planning on going into physics in college, it might not be a bad thing to try to read through. But with his description of entropy, he said his book is about 2 million words. So if you were to sit there and memorize every single word in its exact entirety, where it is in the book, page number, what it means, all that lovely stuff, then you would probably expel, I can't remember the number he gave. Let's say 2,000 kilojoules of energy trying to get that all memorized and stored properly in your brain. Now, the problem is that even though you have created that order inside your brain, in the process of reading, of sitting there and comprehending, your body has given off enough heat to basically be about 10 to 20 times that amount. So, even as you're trying to organize things, you're doing work. As you're doing that work, there's going to be an energy transfer with heat lost, increasing the overall entropy. So even as you are cleaning a messy room, you are still aiding in the universe's tendency to head towards entropy. Okay? Now, second law of thermodynamics, in any cyclical process, the entropy will either increase or remain exactly the same. So, entropy is the variable S. So the change in S, the change in entropy, is going to equal the heat over the time. All right. Now, These are just 4 different definitions of what it is. A state variable whose change is defined for a reversible process at t. Oh, I'm sorry, t is temperature. I apologize. Lowercase t is time. Process at some temperature where Q is the heat absorbed. A measure of the amount of energy which is unavailable to do work. In other words, the heat that has to be lost. Measure of the disorder of a system. Measure of the multiplicity of a system. Now that has to do with paths. We are not going to worry about that guy. Now, since entropy gives information about the evolution of an isolated system with time, it is said to give us a direction of time's arrow. Now, this is another reason last year we had talked about time travel being improbable into the past, but it is probable going into the future. Literally, the second law of thermodynamics tells us why we cannot have things going backwards in time. The universe will head towards disorder from order. So think about it like this. If you have a glass cup sitting on the edge of a table, you knock it off of the table and it is going to basically shatter on the floor. Pardon me. Now, it will always tend to disorder. You are not going to have shards of glass falling off of a table, landing on the floor, and turning into a cup. So basically, it is always going to go from some order to a disorder. Okay? Could be implied that a state came in later time, blah, blah, blah. Don't worry about that. Unless you really want to read Hawking's book, this statement right here is not going to make much sense. All right, for an isolated system, the natural course of events takes a system to a more disordered or higher entropy state. Okay, now a reversible process is going to be a reversible process, a reversible process is going to be a process in which the entropy of the system remains exactly the same. They can happen, they are not too often. All right. In every other situation, the entropy is going to increase. So you may want to jot that down. In cyclical processes, the entropy can remain the same. In reversible processes, they will remain the same. In non-reversible, the entropy will always increase. Basically, this will always tell you what direction time is going, because it is always going to go from a low disorder state to a high disorder state. Okay? So, that is entropy in a nutshell. Okay? In real life, we have the 2 situations here. We've got number 1 with heat engines. And with heat engines, there were 2 things. 100% efficient is not possible. And secondly, Carnot is the best possible. And then through refrigeration, there's nothing perfect. All right, now let's look at the overall situation here and compare it to these real life ones. All right, the chaos has to increase in any of these situations. Now let's look at that heat engine situation. Now, in a heat engine situation, the entropy always has to increase. So that means that disorder has to increase. Here's the question, why? Now the answer is going to come back to one of the same old situations that we've dealt with a lot. The first big reason is friction. All right? With friction, you can never completely eliminate friction. You can get it very small, but you can never completely eliminate it. Now, one side effect of friction is heat. Now, in other words, there's always going to be some waste heat, and that waste heat is going to lead to more entropy. Now, it's also easy to think about this in terms of where you're putting the engine based upon the low temperature dump. We cannot dump heat at absolute zero. Well, I'm going to say permanently. No matter what, you need to dump the heat in some reservoir. That heat needs to go somewhere. It needs to go at some lower temperature. We are going to be limited based upon what we have available. Can we get close to absolute zero? Yes. But the problem is, to try to use that as the low temperature dump for a heat engine means that in a very short time, that temperature that was near absolute zero is no longer going to be anywhere near absolute zero. Right? Your best bet is to dump that heat into a large reservoir, either the atmosphere or a large body of water, which will stay at a relatively constant temperature. But still, that gives us some low value that we have to send it to. All right? 100% efficient. Means that we are dumping our waste at 0 Kelvin, which we can't do. We can't do permanently. We cannot do for an extended period of time. As soon as you start dumping heat into a 0 degree Kelvin situation, it's not going to be 0 degrees Kelvin anymore, or 0 Kelvin. All right? Now, with the refrigeration, situation, all right, heat always flows from high to low. That is the first law. So literally, we cannot expect heat to naturally flow from low to high without any outside work being done. In other words, it cannot be spontaneous. All right, it is not spontaneous. We cannot just let it happen. There has to be work done. Because it is not spontaneous, you need work. All right. So, those are all of the situations in the second law that you will have to deal with. Pardon me, we are not going to be doing much, if any, math with this at all. This is going to be the last topic of this chapter, but I do want to talk about one thing very briefly, and that is the third law. Now, a lot of classes are not even going to talk about the third law of thermodynamics because it is almost useless when we are talking about real-life situations or situations that you can even do in a classroom setting. Temperature scales, thermal expansion, conduction, isothermal entropy, Boltzmann content, first law, second law. Okay, I lost the page I was looking for. Let me go back and do a Google search here quickly. Well, here. Well, basically, the third law of thermodynamics. Let me get you a decent definition here. Go chemistry. Basically, it says that we can never, no matter what we try, we will never be able to get to exactly absolute zero. So the definition is the third law of thermodynamics states that the entropy of a perfect crystal approaches zero as the temperature approaches absolute zero. So first of all, we can never eliminate entropy. Entropy has to increase. So if we were to try to take a crystal down to absolute zero, or any value, any item down perfectly to absolute zero, that means that we would have to decrease the entropy of a situation instead of increasing it. Now, we can send that entropy into a different body, but we can never completely remove it. Okay? So that's the basics of the basics involving entropy. Okay? So both the second law and the third law have to do with entropy. And the third law has to do with crystals nearing absolute zero. Alright, crystals near absolute zero will have nearly zero for their entropy. And this is kind of a side note from it. This is the overall definition, but the side note of it and kind of the implications from it are that when you approach 0 Kelvin, you can't get here. We have gotten to about a millionth of a degree Kelvin, but we have never been able to get all the way down to absolute zero. It is likely that that is a complete impossibility due to the third law. Now, the second law is the big one. The first one is kind of obvious. The heat, in a closed system, delta E internal equals Q minus W. Then you got the zeroth law, which says that if A is in equilibrium with B, B is in equilibrium with C, then A is in equilibrium with C. But when you go here, the second law is the big one, right? Because it has to do with the entropy of the system, and it explains why things will go in one direction, right? Hawking also used this explanation with the second law. If you took a jigsaw puzzle, shook up the box, and dumped the box into the table, is there a chance that the entire puzzle could be 100% put together piece by piece 100% perfectly? And the answer is yes, there is a chance, but the probability of that is very low, because entropy is going to tend to go greater. Rather than it being more and more together as you shake it up, it is more likely to be more and more separated, right? And then the third law just says that as you get closer to absolute zero, you're going to come close to zero entropy, and you can't decrease it. It can stay constant or it can increase. Das ist alles. Now, have any questions, any problems, let me know, but this is more conceptual. What is going to end up happening is, please come up with any questions that you have regarding this. I know this is a complex topic. Let me know if you have any problems, and I will be happy to help you out. Otherwise, we are looking at a test towards the middle of next week. Pick up a study guide in here on Monday. Best of luck on the study guide, and let me know if you have any questions regarding this. Good luck.